Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Let's get started again. In the second half of today's morning session, we have 4 contributed talks, 20 minutes each, including questions. And the first speaker is David Hogg. He's going to talk about going beyond MapReduce and going beyond maximum likelihood.
Thanks. Okay, so this is a slightly odd talk because it's not results, it's not even a proposal, it's a statement that where we're currently going is, I think, in the wrong direction, and it's a challenge to the people in the audience. We've got good people in the audience, so really I'm pitching a project to the world. Hope somebody picks it up. So there's this MapReduce framework, and I will say what that is, although I actually think most people in this room know it better than me, so it's a little embarrassing if I say anything about it, but I'm going to say something about it. There's this MapReduce framework, and it does tasks in log n time when you have huge data, and so it's really important to data centers and to data analysis and to all big data companies on the web. And we can do things like maximum likelihood analyses in frameworks that look a lot like MapReduce. They're not exactly. Oh, and by the way, when I say MapReduce, I don't mean anybody's product. I mean these operations of map and reduce, which I'll say in a minute. I'm not talking about MapReduce, a commercial product. The bad news is that we cannot do the things we need to do in the next generation of astronomical surveys in MapReduce. This will not work. We need to do something different. And we don't know how to do the things we need to do at scale. We don't know how to do things in less than polynomial or exponential in time, exponential in the amount of data we have. And there are people on these various projects here, and they might disagree with me, but I think they have the limited view of what their data analysis will be. I think if you really think about what you want your data analysis to look like, you won't be able to do log n operations. So this is a call to arms, but I might point out that if you solve any of these problems, you might get fabulously rich. So it's not just an astronomy problem, of course, because lots of people are stuck with scale. Okay, so I have various collaborators. Bovey was a student of mine. Brewer is a statistician at Auckland who's very good with sampling and Bayesian things. Fergus is a computer vision faculty member at NYU. Foreman Mackey is my student right now. Goodman is an applied mathematician at NYU who works on applied math relating to data analysis. And Lang was my student, is now a postdoc at CMU, and works on astronomical imaging. Okay, so this quotation at the top here. We won't even consider any algorithms that can't be written in the MapReduce framework. I've heard that said, with small modifications, by people at Google, who say they will not run things inside the house that are not MapReduce, and also at IBM, the Watson team, and those people say we won't do anything that isn't MapReduce. And the reason, of course, is they need to be, think of Google searching the whole web, Watson also searching the whole web in a different way. The amount of data is so large, you have to work log n. You can't work slower than log n. So what do I mean by MapReduce? What I mean is that you split your data analysis into these 2 steps. The first is a map step, where you run the same operation on every piece of data. And then the next is a reduce step, where you then combine pairwise all the outputs that you got from the map step. So this is the way all log n algorithms look, because you have a tree, you do some operation at the leaves of the tree, and then you feed the information back up through the tree. And if you have n things, n leaves in your tree, then you have log base 2n branches. And so you can do operations in this form in log n time, because each of your leaves is sitting itself on a computer. You have a data center, you have your data all over the data center. Every datum you have, every piece of data you have is sitting on a CPU. So you can do all the map operations locally, and then reduce just goes up the tree. So that's the map reduce. I'm explaining it badly, but that's because it's not really my business. In fact, as I'm about to say, none of the problems I work on actually fit in MapReduce. But the way to think about this is, like the standard thing is web search. You search every document locally for the word kittens, and then if it has kittens, you return the document ID and the page rank, and then in the reduce step, you're comparing all the page ranks you're seeing. And so in log n time, you can return the top page ranked page that mentions kittens in log n time, and you've searched the whole internet. OK, good. It's brilliant, but it's also a huge opportunity. That statement at the top means there's a huge opportunity for somebody who wants to get rich. I am not that person, but all the reasons that we can't work in MapReduce is also reasons that lots of interesting companies can't work in MapReduce. OK, good. So here's an example of something you can do more or less in MapReduce. It's not exactly MapReduce, but it's the same kind of structure. Say I have a likelihood function. Do I have a little pointer? Ah, yes, I do. That work? Yeah. So say I have a likelihood function that looks like this. I want the probability of my full data set given some parameters. This is a standard thing for astronomy. And also standard is imagine the data are independent. So these are say these are observations of quasars, tons and tons of quasars you've observed here. Each quasar has a probability given the parameters of your model. But you really want to set the parameters of your model using all the data, so it's this massive product over all your objects. And if you think forward to, I'll talk about the scale, but this could easily be tens of billions of astronomical objects here. So if you want to find the maximum with respect to theta, you want to do maximum likelihood, it's really straightforward. In the map step, for each data point, you compute the derivative with respect to the parameters. In the reduce step, you just sum up those derivatives. And then you can go uphill. And OK, you actually have to, if you want to go to maximum likelihood, you actually have to run some algorithm, some optimization algorithm, like conjugate gradient or BFGS or something. But each iteration in that only takes log n time, because in each iteration, you can compute the derivative in this MapReduce way. So this is a very nice problem. You can do it all in MapReduce. So if astronomers are happy with maximum likelihood and that's all we need forever, we're fine. We're absolutely fine. Of course, I'm going to say that's not true. So what is, just to get the scale of astronomy is not nearly as large as the scale of other industries. So I don't actually think of astronomy as being all that large scale. I spin a large fraction of all of the astronomical data that's ever been taken just in New York. So it's not, we're not talking about Microsoft scale here, but it's big enough that we care about scaling. So if you think forward to LSST, so the two projects I'm going to kind of talk about as my examples are LSST and Gaia. And you might not know Gaia. It's less known here in North America than in Europe. But both of these are at a substantial scale that matters. So in LSST, there's something like 10 to the 15 pixels. I'm right about that, right, Jelko? And 10 to the 10 galaxies-ish, depending on how deep it goes and what cuts you make. But it's this scale. And what we want to do, well, there's many projects you want to do with LSST. It's an absolutely amazing source of science. And I won't summarize it. I'm only going to talk about weak lensing because it's a good example to discuss. In weak lensing, what you want to do is you want to measure the shear map, the distortions of all those galaxies because of gravitational structure formation. So because of the mass map is inhomogeneous, there's this inhomogeneous lensing. So you want to measure this inhomogeneous lensing, and then from that lensing you want to get the cosmological parameters. That is one of the most ambitious projects in all of astronomy, and we have to succeed, or LSST was not such a good idea. So we are going to succeed, but it's going to hurt, as I'm going to tell you in a second. And then Gaia, Gaia is a smaller scale, but the inference problem is even harder in Gaia. Because in Gaia, what you're doing is measuring precisely the stars in the Milky Way, measuring their positions and their velocities. And then you're trying to infer the nonlinear dynamics of the Milky Way from the positions and velocities of the stars. So it's a much more nonlinear problem. So it's actually, even though the scale is smaller, the problem is harder. You want to understand the dynamics of the Milky Way, so the mass model and the orbit structure of the Milky Way. But unfortunately, you have this distribution function of stars. Stars are not distributed on the orbits democratically. Some orbits are more populated than others. So there's a big distribution function problem in here. And the thing that's going to kill us, and the reason that MapReduce isn't going to work, and the reason why we've got a really big problem coming up, is this shear map and this distribution function, and probably also this dynamics, is going to be non-parametric. It has to be non-parametric. The reason it has to be non-parametric is we don't actually know we don't know how to parameterize these functions properly. And what do I mean by non-parametric? So I mean the strict sense of non-parametric, which is that the model gets bigger as the data get bigger. So as you get more and more data, you increase the number of parameters. So your model scale is rising with your data scale. And you can everybody in the room already sees why that's going to be a huge problem. And the reason that all these maps and distribution functions and all these nuisance parameters are going to be non-parametric is that as you observe more and more galaxies, you want to increase the angular resolution of your map. Duh. Like, that's why we're taking more galaxies, so that we can get more resolution. So everything important in astronomy is really non-parametric in some sense. Everything internally in astronomy. I'm actually going to say at the high level we want to get parameters. But in the middle, I'm going to show you some graphical models in a second. OK, good. And importantly, this is an important issue, but I'm not going to talk about it so much. Non-parametric models are never inferred at high signal to noise. Why not? Because once you have high signal to noise, the model grows, you add more parameters, and then you're back down to medium signal to noise again. You never have high signal to noise in a non-parametric model. So by the way, I'm going to show you some graphical models just to set the stage. I don't know if you've seen graphical models. Not everybody in here probably uses graphical models. So if I have a process where I have cosmological parameters which produce a shear map which produces observations, you can think of this as showing the causal relationship that the parameters create the shear map which create the observations. But you can also see this as a description of a probability statement, that the probability of the whole set of all the variables I care about is the probability of the original cosmological parameters, the probability of the shear map given the parameters, and then the probabilities of all these observations given the shear map. See, it's a way of breaking down the causal structure or the probability structure of the problem. So I'm not going to, if you don't know probabilistic graphical models, learn them, because they're incredibly valuable for thinking about data analysis. But now I'm just going to use them as causal structure to look at the problems. So this is the Gaia problem. In Gaia is measuring 1 billion positions of stars. And these are 6-dimensional positions. They're position and velocity. So Gaia measures 1 billion 6-dimensional positions. Where did those positions come from? Well, the star positions it measures are related to the true star positions, and the true star positions are created by the dynamical model of the Milky Way and a distribution function. So these are produced by 2 things. One thing we care deeply about, which is what is the structure of the Milky Way, and one we don't care nearly as much about, which is about the happenstance of what orbits happen to be populated. Now, some astronomers would actually reverse those and say the other one's more interesting. But from my perspective, these are the interesting parameters, these are the uninteresting parameters. But this is a huge non-parametric model. And this might be a parametric model or non-parametric, but this is a huge non-parametric model which is affecting my observations. And I'm going to have to marginalize this out if I want to learn these parameters. That's what's going to hurt. And of course, there's also noise coming in, and there's a noise model. So there's a noise model generating uncertainties, which are also affecting the observations. So you see how this is like a causal model for the Gaia data. And that's the kind of problem we work on. Here's another one. Here's a slightly worse one. This is the weak lensing model. So in weak lensing, you have cosmological parameters. These are the cosmological parameters of the density of the universe, the initial conditions, sigma 8, all those things. They produce a shear map. This is a huge non-parametric object that is our shear map as a function of redshift and angle. So on the other side over here, before we come into the box, over here, there is some distribution of galaxy properties. Galaxies have complicated shapes on the sky, and that generates the true shape of the galaxy. So the true shapes of the galaxies are generated by some horrible process that I certainly don't care about, although I should care about it. And then, but what you observe is not the true shapes. You observe shapes that have been affected by this distortion map. So once again, this has the problem. This has this character that there's this big, nasty, non-parametric model here affecting the observations. And there's a big non-parametric model here affecting the observations. But all I care about is this. I just want to know what are the cosmological parameters. See, this is the structure of essentially all problems in astronomy. Actually, I could argue that this is the structure of all problems in science. I could even go further, but I'll stop at science. I think all quantitative data analysis problems have structures that look like this. And in particular, the thing you care about is separated from the thing you observe by one hell of a lot of nuisance parameters.
What's XN?
That's the position of the galaxy, because in the shear map, you have to know the position of the galaxy to predict its shear. This is overly simplified. The positions of the galaxies are also created by the cosmological model. And in principle, the cosmological model makes this galaxy formation model, which produces the shapes of the galaxies. See, so I've really left out, this is already a massive oversimplification of the true situation. But this is more sophisticated than the analyses people currently do of weak lensing. So this would already be a step in the hard direction. OK, so just in case somebody thinks that we can solve all of our problems with Gaussians, you can't. I don't think I'm even going to say much about this. But the fact is, you never understand your noise properties as precisely as you think you do. And your data are produced by a mixture of processes. Whenever you have a data point, people were just talking about it at the end of the last talk. When you have a data point, you don't know whether that's a correct data point or an incorrect data point. So your data are produced by a mixture of correct and incorrect things. And it can be a lot worse than that. But at the very least, it's that bad. And once you're that bad, every data point produces multimodal things, because there's this classification inside your data point that allows you to jump to two different locations, bad data, good data. And so you generically get multimodal things. You also get very broad support in parameter space, in the sense that a data point, if it's true, is telling you something very useful. But if it isn't true, it has broad support. And so it's very hard to approximate the likelihoods you're getting from individual data points with very compact functions. OK, good. So now I'm to the final point that I want to make. This is the main point I want to make. Bayesian inference cannot be done in this MapReduce framework. And you might think it is, because it looks hella like MapReduce. And I've seen a lot of glib statements that it looks really MapReduce, because you have all the data which are producted together, and you have a prior. So this is like a Bayesian, standard Bayesian inference. You can compute these local likelihood functions. You can compute these all locally, and then only product them together in the reduce step. So it looks really good. You can locally produce your likelihood functions, and then on the reduce step, you bring the likelihood functions together and you multiply them together. It's perfect. In fact, you don't even have to be a Bayesian. Good, you don't even have to be a Bayesian. This is you can just think of the likelihood analysis. You can do this. You might think, oh, good, I can do this all with MapReduce. But you can't. You cannot pass forward those functions. Theta is a very high-dimensional object. The functions are multimodal. The support is broad. And these non-parametrics mean that this might even have a variable number of parameters that's growing with the data. So no individual node knows enough about the whole data set to know how much detail does it have to pass forward in its likelihood function. You have to know a huge amount about the whole data set to say with what fidelity do you need to pass forward this function. So there's basically this fails. And I say, but that's not all, because the other problem is marginalization. We also have to do a massive marginalization, and there's no way to marginalize out. If all I care about is this, and all I'm observing is this, I have to marginalize out this, and I have to marginalize out this. These are big non-parametric functions. And furthermore, their marginalization depends on all the data. After you've observed this, the posterior on this depends on all the data, and you have to then integrate over that. So there's no way to do that locally. Of course, it's necessary. If you don't do that, your constraints on the cosmological parameters will be wrong. One of the things about weak lensing, one of the reasons weak lensing is such a good example is you never measure this at high signal to noise, but you really care about your cosmological parameters. So if you don't do this marginalization, you will fail. There are enormous non-parametric Bayesian inferences that have been done. How did people do them? I just said you can't do them. It takes exponential time or something. I didn't tell you what time it takes. It takes of order n cubed if you just naively write it down. Not log n, but more like n cubed. So how have people successfully done this in the past? The way they've done them in the past is by carefully choosing priors that make the inferences tractable. We are not allowed to do this. Why not? Because we are scientists. And our prior information has to contain our prior knowledge, and our prior knowledge won't be in conjugate form. We actually have non-trivial prior information, so we can't do this. So these Bayesian non-parametrics, if you look at Bayesian non-parametrics, it's almost useless to us, unfortunately. So and my view is that the word Bayesian is becoming a bad word. My approach, I don't have an approach. That's my approach. But I think this is the issue. I think the next generation of surveys will fail if we don't solve some of these problems. I have to say, the applied mathematicians and the computer vision people know a lot of really great things about these kinds of problems, and we should be working with them more. All my collaborators, if you notice, more than half of my collaborators in this were not astronomers. That's been extremely valuable to us. And there are people in this room, of course, who have also drunk that Kool-Aid. In my day job, just to say I'm not a total bullshitter, I do big models. Right now we're building a 10 to the 9 parameter model of the SDSS pixels as a kind of baby step towards LSST. We are getting some Bayesian non-parametrics working, but with real priors that represent our knowledge. We have one of the best adaptive MCMC samplers around. If you need some MCMC sampling, we have both Brewer and Foreman-Mackey are my experts. We have done full marginalization of a non-parametric distribution function, but of course in this problem we only had 8 stars, not 80 million stars. We've done huge models of data-driven models and made large predictions, and we're big believers in working with missing data and heterogeneous data. And I'm done.
Okay, questions?
Two comments, I think, David. Firstly, there's this new stuff coming out of Google now called Dremel. I mean, we all know MapReduce originally came from Google. Google have done away with that now. They're using this new framework called Dremel, which is supposed to be beyond MapReduce and scale up to web scale problems. Can you comment on, have you looked at that, or does that solve something?
No, so I haven't looked at it, but I'm almost certain that they still need log n. And so nobody is doing a marginalization, basically, in log n time, because I think it's, so I haven't looked at it, is my basic answer, but I very much doubt it will solve these problems. This will be a real breakthrough, because if people can solve the problem of passing forward the posterior probability through some log n thing, that would really be game-changing. Like, new companies will appear the next day. But I have to say, there is one respect in which people have done this in log n time, and you could do, and that is I forget what the name of it, there's a technical name for it, but it's where you build only very, very low parameterized models of the posterior and pass those forward only. And if you can work in that approximation, you're good. I'm just saying that in astronomy we can't work in that approximation. But anyway, yes.
My other comment was going to be that people have translated Bayesian networks into MapReduce.
That's correct.
Where,
yeah.
And that does work.
Yes, and that is exactly in this form. That's this like deep learning. Yes. So in deep learning is one of these non-parametric Bayesian things. So in deep learning you have many layers in like a neural network, and you design that so that all the edges in your graph are analytically marginalizable. They're very beautiful models, actually, to be fair, and they're extremely high performing. Like many of the best computer vision algorithms use these deep learning networks now. And deep learning, like there's now on-chip deep learning, and it's amazing. But it really doesn't work for us. It works really well in the world, but it doesn't work for us because our priors are so specific. Like our priors on that shear map are very specific, so we're just not allowed to use these tractable priors.
Okay, in the back.
I really enjoyed your talk, and I agree with most of you said, but there was one statement that made me almost fall off my chair.
Uh-oh.
You said that if we don't solve this problem as you phrased it,
Yeah.
that the future surveys will fail,
Yeah.
which I think it's a gross overstatement. I do agree with you that without sophisticated non-parametric models, we might not be able to extract the entire information content of surveys like LSST, but even using contemporary methods, and
Yeah.
we'll definitely have better methods a decade or two from now, we can still extract significant fraction of information in these surveys. And I don't know quantitatively how much better you would do with non-parametric models, but I do know for a fact that even with standard methods, we will get enough information content that we cannot claim these surveys will fail.
Good. So let me be a little bit more specific. The LSST, without solving this problem, will meet its goals. But in my view, that is not sufficient because we're spending a lot of money, and we should be. And the current plan with LSST. I mean, if you do not solve this problem, you're in the state of classical statistical estimators and all the argument about bias and variance and so on. So most of the weak lensing literature right now is people arguing about minor differences in how they estimate shears to look for unbiasedness. And as the survey grows, the sensitivity to those biases and variances will grow. So it's not obvious to me. So I agree that LSST will meet its goals without solving this problem. It will meet its stated goals without solving this problem. But it is possible that there are systematic problems with all the point estimates people have for this problem, such that LSST will drift into a systematics-dominated position on the weak lensing.
That the complexity grows linearly with the size of survey. That is perhaps true in non-parametric models. But for example, if you just use the extreme deconvolution, as you increase your sample size, the number of components you resolve does not increase linearly with the data size.
That's true. One thing that might help a lot is it is possible that the complexity of these models might only grow as like the log of the data size. And in that case, that might save us. That might save it. It's still the case, though, that this marginalization is very hard. The marginalization is still hard, even if it gets, because the marginalization itself is expensive operation. But it is true that these may only grow as the log of the size of the data. That's not a known scaling yet. That's right.
I hope to accept, but time is running out, so please ask him during the lunchtime. So I'd like to move on to the next talk. So before that, let's thank to the speaker again. Next talk is by, what's your first name?
Nebojša.
Nebojša. Jožic. His talk is titled as Epitomes and Counting Grids, Discovering Patterns by Rearranging feature counts.
Okay, so I'll talk about a very simple model. And since you guys are astronomers and looking at images all the time, maybe this is not that new to you as it was in the computer vision community many years ago. So I'll talk about a very old model that I've introduced many years ago, and then an extension that's more recent. These models have been used also in other applications. We've used them for vaccine design, we've used them for viral load prediction, and so on. Now, the basic idea is very simple. You'll very soon see why I chose to talk about this particular area, which is not actually what I'm spending most of my time today, but I mean these days, but it may be most relevant to your problems. So the idea is very simple, and I talked about it briefly the last time we had a similar workshop several years ago. Let's say you have an image, my mother's poodle, for example, and let's say that I want to somehow summarize the texture of this image, the repeating patterns in this image. And the way that I would do that is to take at random lots of different patches of different sizes from this image and then try to assemble them back. But I will assemble them back into something that's much smaller than the original image. If I'm able to do that, then obviously I will have to somehow squish all that texture so that instead of having all these flowers in the background, I'll have only a couple, which is actually what happens here. I have a couple of different types of flowers, a little bit of area here for the gravel, and some area for the fur, and so on, which means that I've kind of learned the structure of the image. I know what the self-similar parts in the image are. right? I can now do segmentation, for example, of the image by segmenting this out here in the epitome and transferring that back by inverting the process, finding out what this area came from in these images, and then in these patches, and then where these patches came from the original image, and then segment out the gravel, for instance. So again, the idea is that if I take all these patches, if I just look at the patches here, I can't really reconstruct the entire image back without knowing where they came from, but I can see enough of common structure that I can learn a squish texture. Now, how would I learn that? Well, the approach is very simple. I would start with some guess, and this is what we call the epitome, this little squish texture. So I'll start with some guess of that epitome, which is basically just the average color in the image with some noise to break the symmetry. And then I'll take all those patches, see if I can map them there, and they will initially map equally well or equally badly to all parts of the epitome, but some parts are going to map a little better. And then I will count all the times that I've hit every pixel in the epitome with these patches, and then average those pixels based on how often they've hit there, taking all the probabilities into account. And then when I do that, I'll, in the next iteration, get something like this, where you can see a little breakup of a little whitish part to the left and right, and black in the middle. The reason why you have whitish to the left and right is because the epitome is actually defined on a torus, so left and right connect, and the top and bottom connect. So then if I keep iterating this, after a few iterations, and here I'm showing 16 iterations, you get this texture that I've shown in the first slide. So that's basically the algorithm. Now, the question, of course, is, what do I mean by mapping the patch into the epitome? I could introduce some kind of geometric shears or intensity manipulations or rotations and shifts and so on, or I could just map the patch as it was. And of course, if I do all these transformations, then I have to keep track of them when I'm re-estimating the epitomes. And then the other question is, am I always going to get the same epitome? Obviously not, because I have this random initialization, so I'm going to get different epitomes. So, but they'll have a qualitatively very similar appearance. So to demonstrate that, here's the epitome of Microsoft Research as it was, I don't know, maybe this might have been, I don't know, 7, 8 years ago. Different building, as you can see. So the epitome here has a lot of these elements that are window elements, because there's a lot of them in the image here. And it has a few faces as well. And probably most of these faces map to either this one, or maybe this area here, or the area there. But if I rerun this, I'll get a slightly different epitome. So here I'm kind of zooming in into this one. But qualitatively, it's very similar. Again, I have some face-like thing here. I have a face-like thing here as well. And in this area, I've put red and green on either side of the nose of the face that appear there. And then I mapped back from the epitome through the patches into the original image to see which areas contributed to this area. And I get a face detector from just one image of Microsoft Research. It doesn't work like the best face detector, but still, it's just one algorithm that does it. Simple one, simple iterative thing. If I do an epitome of many different faces, then I get this weird facial texture. It's bizarre. But if I now highlight, for example, these 3 areas here, because I see a little smile here, I see a closed eye here, and I see some dark hair there. So if I pick these 3 things and I look back for all images that map there, whose patches map there, I get these guys who have dark hair and tend to squint when they smile. If I instead choose this other type of an eye, I get these guys who actually have their eyes open when they smile. So this is where the vision comes in, right? The computer vision. And there's a lot of other applications that I don't have time to talk about. Epitomes were mostly used by computer graphics and computer vision people, but they've also been used in vaccine design. But here is the thing that I've always found most exciting about epitomes, but I've never been able to apply them this way. Here's an image with a lot of structure. Do you see the structure? You can't quite see the structure, and if this was some scientific image, you would just assume that there isn't anything there. You wouldn't model it at all. But when you run the epitome on it, it actually finds that there is a lot of 45 degrees lines this way and that way, and that's because that image really did have that, but it was obstructed with lots of noise. So the idea here is that if you run this algorithm, since the epitome is taking all these patches from everywhere, trying to match them, then average them, as you repeat this, the obscured patterns arise. Now, this is an artificial example because you never find images that are this corrupted. Here's an example where that's the closest. It's electron microscopy example. But in this case, the images are actually controlled. They have very fine control over the microscope, so it doesn't move too much because the noise is humongous. So then a video is taken instead of just one frame. So here are these videos, and then you average them. But even a slight shaking of the microscope creates a little bit of blur. So if you use the epitome to do what to actually compute the shape there and reconstruct it, you get much sharper boundaries, but also you get structures that were obscured before. But as I was saying, the more interesting example would be if you can actually have something like this, where the patterns appear all over the place. You have some huge amount of data coming. You can't see them. You don't know where they are. They're obscured by noise, but then by averaging, repeated alignment and averaging, you reconstruct the pattern. Another example where these things can work well is if you have missing observations altogether. So in this case, I'm talking about a 3D data, a video sequence. And the idea is that data was missing. For example, if the data is missing every other pixel, that's equivalent to trying to actually, and you're trying to reconstruct it, that's equivalent to doing upsampling for super resolution, increasing the resolution of the image. If the data is missing in a rectangle like that, I mean a solid like this, then you're trying to fill in the data there. If there's something missing completely. If it's missing in different frames, then you're trying to interpolate the frames. And I'm going to show an example which doesn't really exist in practice, but again, to emphasize where these algorithms will have the most impressive use. Here the data is missing at random. There are a bunch of different places where the data is missing, and it's replaced by random noise. And then if you use this algorithm to reconstruct what's there, you get this. So I'm going to pause it here, and when I run it again, you will probably see this car moving around, but you will definitely not see the pedestrian. So I'll play it a couple times. So when it comes to science, I'm thinking that a lot of times, the first thing we want to do is to look at the data. And if we don't see anything at first, we're not even going to run the algorithms on it. And some of these algorithms are better at finding patterns than we are. In computer vision, that's not the case typically, because computer vision algorithms can't beat our vision because we've been optimized for it. But in science, there may be an application. Now I'm going to switch to this other model, which we call counting grids. And it's a relative of epitomes. In the epitomes, we were using matrices, ordered data sets. They could be ordered set. Each data point is actually a set of measurements, but these measurements are coming on a grid. So either it's a two-dimensional matrix or a three-dimensional matrix. So there is some ordering there. In the counting grids, on the other hand, we have disordered feature sets. So for example, if you imagine all those patches that I was showing you before, and you don't give me the patch itself, you give me a histogram of colors in the patch, and that's all I have. Now the question is, can I still reconstruct the image? In both of these cases, of course, the number and type of channels is arbitrary. We don't have to have just RGB measurements. It could be features of any kinds, measurements in different spectral domains and so on. Now, where do we have these histogram-like data points? So here's one example. In the cellular immunity, what we have is that the cell expresses all kinds of proteins. We heard about it yesterday from David. So there are all kinds of proteins that are being expressed, and they're working in the cell. They're regular, normal proteins. But sometimes you get viral proteins as well. And for the cell to actually figure out that something is wrong, there are some mechanisms, and it can try to fix that. But these viral proteins look a lot like normal cellular proteins, and it's very difficult for a cell to self-diagnose. So then there is this more global approach to this, where the cells actually, as they're expressing these proteins, they express a lot of the copy of the same protein. But a certain small percentage of these proteins are going to be chopped up, and little pieces are going to be presented on the cell, on the surface of the cell. And then these little pieces are now visible to the outside of the cell. And then the immune system actually monitors through the use of T cells, specialized surveillance cells, that they monitor all cells around. And if a certain pattern that seems abnormal keeps repeating, then the immune system might go and start killing cells that have a certain signature on the surface. So what does that signature look like? Well, it's basically, as I was showing here, a bag of epitopes, a bag of these little peptides as presented by MHC molecules. So in the end, because we don't know of any ordering of these things on the surface, they just come out on the surface in certain spots. There is no particular ordering. Really what we have is that we have 2 of this type and 1 of this type and, I don't know, 2 of this type and so on. So it's basically a count of different features that are present on the surface rather than the organization of them in some 2-dimensional, 3-dimensional, whatever structure. So in the end, what we have is a histogram. We have features, in this case, 20-something features. And we have feature counts for each of those. And this type of data is present in various different applications. For example, documents on the web are represented by a bag of words rather than a document most of the time. It just counts of how many words of different types you have. In computer vision, actually, they've started doing this because there's a lot of problems with aligning things. So they try to instead find very informative features and that disorder them completely. And then a similar thing obviously happened in case of immune surveillance, as you saw before. So what's the model for this, the counting grid? Well, we start with a peaky distribution because just like in the epitome, we're going to have a grid. And in each position, we're going to have, instead of one color or a sharp distribution of colors, we're going to have a sharp distribution of features. So we start with a peaky distribution. It goes into a particular spot in the counting grid. And the counting grid is going to have a lot of these different distributions, all peaky with respect in comparison to what the data is going to have. And then the idea is you take a window, you put all these counts together, and that's what you're going to see in your data. So that's the generative model of the data. And what that means that, for example, if it's a 3x3 patch that you're taking from the counting grid, then your histogram in this particular example looks like what's shown. But then if I move the patch a little bit, then I have some features disappear, those that are on the left over there, and others are included. So you have this smooth transition of feature counts. So then this is the summary of what the generative model looks like. And then, of course, the learning algorithm is going to be similar to what I talked about before, except that now not only that you have to map these bags onto the grid, but you have to take the individual features and map them inside the windows where these things are mapped. So you can iterate that and get something. So here's an example, a synthetic example, where we are pretending that the computer vision algorithm has somehow found features that are very informative. So it can label things in the image as being mountain, sky, grass, building, roof, and so on and so on. And then if you take one of these windows, you just get a distribution of features. So in this case, for example, there is a little bit of a roof, but a lot of the mountain and the grass, for example, and a little bit of a sky. So now the question is, can I just from these histograms infer things? Or if I can from the histograms, how about if I take each one of these patches, break into 4, and get 4 histograms for these different parts? Would that be enough for me to reason out what the original layout of all these things was? And I'm using this not because it's useful as it is, but because it can give us the idea how much it's possible. Is it possible from histograms to infer the spatial arrangement of features? It turns out it is. In this case of a 2x2 tessellation, we get this as a reconstruction, whereas the original looked like that. So it's pretty close. And here's another example where I'm working with colors. I took this image, discretized into 64 features. So I have, I don't know, one feature would be blue, another feature would be another hue of blue, and so on. And so I have 64 of them. And then in this case, I'm trying to learn the counting grid. And of course, I'm showing in each part, each cell of the counting grid, what's the most likely feature. And in this case, I'm trying to just learn it from histograms alone. And as you can see, after a few iterations, I start getting something that captures some of the spatial structure, but it's difficult to get the spatial arrangement, which is great. So I do get I do infer some neighborhood information. The certain features tend to border some other features, but I don't get a very good structure. But if I do a 2x2 tessellation, so that each patch is represented by 4 histograms for the 4 quadrants, then I actually do reconstruct the original image. And then if I do a 16x16 tessellation, since the patches themselves were 16x16, I'm actually reducing this to the epitome algorithm, and I reconstruct the whole thing. I will skip the application here. I'll just tell you how you can use it now for analyzing the viral load in HIV patients. So as I said here, we're going to model these bags of epitopes using this model. And so once we've learned the model using the bags of epitopes, which are actually inferred based on the immune type of the patient and their sequences, so we know what's presented on the surface, now we can take every patient and put it somewhere in the counting grid. Now let's assume this whole screen is the counting grid. Now this particular patient maps into this window, and I just put blue here because they had a low viral load. And this other patient had a high viral load, this one low, another one with a low viral load, and so on. If I keep on placing them like this, hopefully the high and low viral load areas are going to emerge. And I can do that, again, by averaging viral load into these windows. And when I actually do that, this is what I get. And this is for various different parameters of the size of the counting grid and the patch that I'm using for embedding, because now I have to choose how big my patch is. The actual histogram of features doesn't come with any idea of how big the patch is, but I'm pretending here that it's 22 by 22 patch size, and here it's 11 by 11. So I'm rearranging all the features and then figuring out the counting grid. And this is an example of a 3D version of the same thing, because I don't have to embed it in 22 by 22 patch. I can embed it into 10 by 10 by 10 patch. So I can use an arbitrary embedding. It turned out, actually, that the 3D embedding was the best. And so here's, after a few iterations, you can see how the features how the viral load starts separating. And it turned out that it works actually better than other techniques we've tried to use for viral load prediction. This is an example that I'm not going to talk about of using this to model text. This is a model of all the NIPS papers. And here's the summary. I already told you what the difference between epitome and counting grids is. But the opportunity, I think, is discovering of patterns in seemingly complete noise, under the assumption that there is a pattern that repeats a lot, but it's misaligned. So you can't use Fourier analysis to find the repeating patterns. And this is that example that I gave you before. So that's it from me. Thanks.
Okay. Question?
Do you think this epitome-based approach could be used for doing super-resolution imaging? Like, for example, if you have a video of a car going by, grainy video, could you this license plate?
Yeah, we've done that actually. We've done it on grass waving in the wind, and it works way better than traditional techniques. But the artifacts are very, very weird. But the sharpness is way higher. I can show you that offline. Yeah. Mm-hmm.
Okay, go back.
Can I apply this to astronomical images?
Mm-hmm.
Big like maybe galaxies or something?
I don't know. I have no idea. I don't know much about galaxy images. So that's why I actually showed it like this. So I'm hoping that you guys can tell me. You can come up with some applications.
What is your text application?
The text application is the one we've tried a couple different ones. One was this NIPS data set where we have all the papers from published at NIPS with all the words in them. And then if you now try to infer what would the arrangement of these words be in a 2D little patch so that it belongs to one of a large counting grid so that there is a smooth transition and so on, you get essentially very interesting areas occurring. For example, computer vision is sort of surrounded by graphical models, neural networks, and neural science, because not surprisingly. And then reinforcement learning is bordered by neural networks, which are also HMM because of the time models and the support vector machines. And actually, when you move from when you look at the documents, you can clearly see how this smooth transition is happening. which is very interesting. It would also be interesting to look at this if you're trying to choose your area of research in IPS. You're going to see where the boundary is not populated too much. So that's one example. The other example are the news, especially the news, especially because there is this transition. There are multiple topics that are evolving over time. So you really see how words are dropped and new words are put in, but they don't necessarily really follow a one-dimensional structure, but multi-dimensional structure. So they capture, for example, CNN news better than the LDA models, which are traditionally used for modeling bags of words. Yes?
Quick.
Quick question. You have a generative model in astronomy. If we apply it in astronomy, we often know a lot about our noise processes. Are there ways to modify the algorithm so that it can know about all the noise properties that they know?
Yeah, obviously. I mean, you could think of this as just a part of that graphical model you've shown in places, especially the non-parametric parts, for instance. But yeah, you can definitely add all kinds of bells and whistles that depend on the prior knowledge. And on the other hand, if you know almost nothing, or you want to start afresh and you don't want to make presumptions, then you can learn non-parametric. Because this does end up being a non-parametric model, you would need larger pyramids if you have much more data.
Okay, thank you very much. Let's move on to the next speaker, Giuseppe Longo. Practical data mining services for astronomy.
Well, I think most people in the room know what I'm going to talk about, since this has been the dominant theme of my talks for the last 5 years, with many evolutions. And this is at some point, you start changing the title, but the substance doesn't change much. I'm going to talk about data mining and about a project which has been going for many years. It was a sort of pioneer in the context of the virtual observatory. At the beginning it was called VioNeural, then it became DAME, which stands for data mining and exploration. But due to some delays in the implementation of the standards which we needed, I mean, at the beginning we were all pioneers in the virtual observatory. The DAME has never become a real virtual observatory complying device, but I think that now that all the pieces are where they must be, the transformation could be done quite easily. DAME is a joint project between my university of Naples, the California Institute of Technology, George, and these dudes, and the Italian Institute of Astrophysics, INAF. I mean, it has had many collaborators over the years, then given the specificity of Italian situation, most of these collaborators have emigrated, and now they are in this room under different heads, but it has been a thing which has been going on for many years, let's say. And, what is DAME? Actually, I have a system manager who is fanatic about acronyms. So DAME, what we used to call DAME, now it's DAMEware. DAME is a general platform where we are putting all the web application which we are implementing over the years. And as you can see, there are quite a few things. I mean, now we have applications of text mining related to the globular cluster. So it's a web application for updating all knowledge available on globular cluster. I'm not going to waste much time on these things. And now we also have opened the new section for the Euclid mission data quality, because our group was put in charge of this thing. And, but what matters is DAMEware. DAMEware is a DAMEware web application resource which is aimed mainly at data mining in astronomy. Everyone from anywhere in the world can access an infrastructure through a browser, because in fact it is a web application. You can access an infrastructure for data mining where the computing infrastructure is completely transparent to the user. I mean, the web application decides where it is better to run the application as a function of the size of the data and the complexity of the problem. And you have a series of models which can perform classification, regression, clustering, feature extractions, which are the typical data mining applications. These models are, you see their list, which is quite complete, I would say. We have many methods for regression and for classification. We have some methods for unsupervised clustering. Others are coming in. And the next to be implemented, which are in the process of being implemented, are the Bayesian networks, the random decision forest, and another version of a multi-layer perceptron. I'm not, actually, since I've been speaking so many times of these things, I'm not going to waste much of your time. I just want to point out that besides, it has been often said that we must prove the utility of the work which have been done over the years with the real scientific results. I never understood well this question. I mean, why to prove the utility of infrastructure you need to have the killer app? This is something which is completely out of my mind. Most of our life, most of our careers, most of our work is about simple contributions. I mean, about producing papers of honest, decent work where you just make a measurement better than others or you improve upon something. I don't know why by these types of AstroInformatics, let's say, infrastructure, we always want something more. So we made a point of trying, I mean, we opened basically a call for collaboration with the community for good cases where to use this platform, DAME, to solve problems with the data mining techniques. So basically, I don't know what is my role in this moment, if a data miner, if the principal investigator of the project, or as an astronomer. I don't know anymore what I am, and I think this is a problem which I never solve. But in the last few years, also due to the fact that there was a cut in funding and overall in Italy, I mean, about 60%, we stopped improving the infrastructure. We couldn't do any development. We began to apply the existing infrastructure to a series of programs with the results which, to my opinion, are quite satisfying, since basically with the minimum effort, in all cases, we always have achieved the results which are much better than what is available in the literature at that moment. And I think also with the smaller effort. I mean, we have been working on massive data sets on the whole slope, in some cases on very small data sets, like, for instance, in this case, where Paulillo Impuzia, a colleague from Chile, wanted to see whether it was easier to separate globular clusters in external galaxies using data mining techniques. And we just applied it, the platform, actually Thomas did from Chile, applied the thing to the problem of NGC 3199. He took 11 parameters, so it's a small data set, a small number of features, something like less than 3,000 objects, therefore a piece of cake for data miners. He used a multi-layer perceptron with quasi-Newtonian approximation for the classification problem. MLPQNI, it's very effective in generalizing from small bases of knowledge. So it's the ideal for this type of problem. And it performed something which is very important to remember when you take into account this type of analysis, is the fact that one of the advantages is that you can perform a feature extractor. So you can plug in as many features, parameters you have, and then let the method itself to evaluate which features are significant, which are not. So there was a first run of feature extraction where the network learned how to recognize globular clusters. So we have to stop for a second. What is the definition of globular cluster? Usually globular clusters in external galaxies are defined using If there are high-resolution images available, like for instance HST, you can use structural parameter plus color. The idea was to use a base of knowledge built upon HST knowledge to try to identify globular cluster using single band HST images, therefore without colors, plus colors from the ground. So mixing very low quality data from the point of view of angular resolution with color obtained from the ground. I mean, I'm not going to spend much time because it's quite complex actually. It needs me sitting on a table checking individual plots together. But basically here on the upper graph you see the selection performed with the traditional method, and here on the right you see the selection performed using a neural network, where you can see there is a much better correspondence between the object identified with the globular cluster with the selection box, which is marked by this dashed line. Other example, we participated with the simple tool. I mean, it used via browser, the one which I mentioned before, to the FAT contest for photometric redshift. This has been a large contest run 2 years ago, where basically all people who had implemented the photometric redshift models applied their method to the same data set, and the results and the statistics were done independently, not by the team who was applying the method, but a sort of evaluation committee. And well, this is the result of the application of the same method. This is the most incredible thing. All you see, I made a choice among all possible cases. I took all the results which were obtained with the same method, okay, with MLP, with the quasi-Newton approximation. Well, and without doing anything, just running the usual feature selection. In this case, we had quite a large number of features, and we had the problem of missing data. In fact, here you see good basically refers to the amount of missing data. This is no missing data in this band. In this band, quite good, which was some percentage of missing data, down to poor. So we just, since we know that neural network deal very badly with the missing data, we just threw away these last two groups of feature, medium and poor. We used only one. We ran a few experiments of feature selection. We had ended up with this combination, so without this feature, and without this feature as the most successful. And then we ran on our training set to obtain our final result. And is what you see here. Against all the method, empirical method of the FAT contest, QNA is our method. This is a table from the paper. I mean, QNA in the 18-band case, which for us actually was this one without this band, because this really convey no information whatsoever, and this is something which none of the other method noted. These bands were just useless. If used, they increase computing time and decrease accuracy. So our results were, in one case, comparable in the 18 band, with what you could obtain with another interpolated image, and the other one, they were by far the best. So even in problems which are, I'm done, really, it's very quick. Another example is this one. This is a paper which is coming out now, which was inspired by a paper by your student, David and Bowie. You applied it to that simulation of, to the mixture of the various QSO. No? We applied our same method to the larger data set extracted by the overlap of Galaxy, UKIDS, Sloan, WISE, SDSS for the quasar, in order to see whether it was possible to obtain a good estimate of photometric redshift for quasar. And again, something which you cannot do easily with other technique. After a phase of feature extraction, we found that the E5 and D16 are by far the most effective methods. So basically, WISE is completely useless for what the photometric redshift evaluation is concerned. And also some ways to measure magnitudes are completely used as well. What we found is this, and then I'm sure you will like to discuss about this, because we are better than you. We go down to 0.101 with a percentage of outliers, which in 1 sigma, 2 sigma, 3 sigma, and 4 sigma decreases very quickly. And we are not using the 70,000 objects. We are using only 8,000 objects. So even without knowing the model, the physics behind, just by using in a proper, rational way, let's say, data mining techniques, you can obtain very, very useful scientific results. Well, they can not be the killer app, but for sure are extremely effective. So very quickly, I just want to focus a few seconds on what are the problems. So, well, if funding will come back to the Italian shores, this is the direction in which we intend to move together with our colleagues at Caltech. And as you have seen, one experiment for each application requires hundreds of runs, because you have to do future evaluation, you have to choose the better algorithm, and so on. So it's most of these algorithms, especially on large data sets, are computing intensive. So if to this you add that you should move a huge amount of data set, I mean, the thing is not going to work. So at the moment, we are trying to define standards to be able to move the web application where the data are. This is an idea which we already suggested a couple of years ago at an IVOA meeting, and but due to the lack of funding, we have not been able to proceed with it. But the idea is exactly that one, to have a set of data mining tools in common, shared by the data repository, and basically to have an interoperability not only of the data, but also an interoperability of the web application. So this is one thing. There are also other directions which we are trying to move in collaboration with others, but really my chairman is pointing out that the time ran out. But I just want to mention that another useful approach is also to optimize the computing time of individual model. We are exploring the use of GPU for a specific model. We have done an implementation of a genetic algorithm, but I think that the real problem is to find a way to standardize this web application in order to be able to move them where the data are. I'm done. Perfect in time, I'm done. So it's
Okay, the papers that you showed were mainly done by people who've been working directly on the development of DAME.
Because this is part of the story, yes.
Are you starting to see more?
Well, Puzia, for instance, a Chilean colleague, Puzia is one of the globular clusters, the one who started the idea. The work on the photometric redshift now is being moved inside the Euclid collaboration, because it will become one of the methods used. You know, it's a slow recognition of. I mean, I must also be honest. I mean, neural network for photometric redshift have been used by many years. So basically, it's easier to accept something which is already common. So the fact that Euclid has accepted data mining methods in, let's say, in that context makes sense. The problem is that there is the usual long-lasting question. I mean, most of the community sees these models as a black box, and therefore as a sort of skepticism about them. And the only way to beat it is just to show with papers that they work. So we are open to collaboration with everybody. So that's, in few words, the history of 5 years. Thank you.
All right.
3 of them, my God.
Okay, thank you very much.
You wait.
last talk in this morning by Josh.
And I'll be accompanied with pianist Chiro when the time comes.
Okay.
So Jim really brought up some very important points about the need for better visualization of data, more natural interfaces, and so on. I think technology is pushing us in that direction, and there's some very interesting things that we can be doing. So I'll show you a little bit of stuff that we've been doing, but as you probably some of you know, we've been experimenting with virtual worlds as a platform for scientific research and collaboration as well as data visualization. And that's basically riding on a technology that's driven by the Moore's law and it's paid for by the commercial world. 3D video is coming thanks to the movies and other entertainment. Games are already virtual reality that all the digital natives have grown up with it and think nothing's more natural. And so, people are paying attention, including people like chief technology officers of Intel, and we have good collaboration with Intel Labs in Oregon on doing this. So this is something that is going to be as transformative as the web itself was, and it behooves us to find out what we can do with it. So today I'll focus explicitly on some data visualization angles of it. There is already a lot of immersive, collaborative, interactive data visualization going on platforms in virtual worlds of different sorts, and not just in astronomy, other fields as well. Mathematical objects, molecules, numerical simulations of globular clusters, numerical simulations of data mining in Intel world that I couldn't bring up. And we already know how to encode up to maybe 10 dimensions in these pseudo 3D displays. One of the new things that our student Franz Sauer has done is that we now can click on individual data points and pull up web pages or archives and other links for information to follow on. So if you see, say, an outlier, find out what is it, and carry on from there. So this has been done using so-called open simulator technology, which has been standard so far, basically, in this business. And it's an open source version of the old Second Life, but that's pretty much dying. New thing is Unity 3D library, with a lot of development with that. Our student Alex Kyok has been doing this work, and Chiro will demonstrate some of this. But first, let me take you to just a quick demo of what we have. So this is the real data display. The data are actually 8-dimensional data set on quasar spectral energy distributions from Gordon Richards et al. What's shown here are 3 XYZ axes are flux ratios, and I don't remember which ones. The colors and the sizes of data points encode 2 other physical parameters, which I again don't remember. And you can fly around this. You can see that objects of different kinds, partly separate. Something like this is really essential if you're going to do proper clustering analysis, because things don't look Gaussian. You have strange shapes and topology. And it can certainly guide proper data mining research. Now, of course, you can have your colleagues join you in this, add the data, poke at it, plot new data. You can switch the axes and things like that. The old one that I have to just show you. This is the one I used for our cover picture. This is, again, data from Sloan on stars, galaxies, and quasars, where XYZ axes represent 3 colors, sizes represent magnitudes, shapes represent kinds of objects, and this was being actually heavily biased towards high redshift quasars. That's what these guys are. And you can see that you can really find out where the outliers are in a much more effective and intuitive fashion. And you can immerse yourself in the data with your colleagues and interact with them and so on. So Chiro, do you want to demonstrate the Dame player now?
Yeah.
So this is done on a standalone platform, but also, more importantly, through the web browser. And so that's what Chiro is showing.
Okay, virtual worlds are great, but you wanted something different. So be able to have a collaborative environment through the browser or even through your tablet. because we can also make app for iPhone or iPad. So we tested a few game engine softwares like Shiva, but we ended up using Unity 3D because we really liked the platform, and we can program in JavaScript, C++, C#, even Boo. So now this is the same data set that I'm going to visualize. It's Aero Astronomers, I can switch to night
point
vision.
out that in the old platform, we can do thousands of data points, and with some effort, maybe 100,000.
Here we can put 100,000 data
easily.
points. Yeah.
Very fast, and we're working towards 1 million.
Yeah, if these things. Okay, and don't pay attention to all these buttons, because this is actually the first time we are showing it, and this is a development version. I wasn't even aware till 2 hours back that I had to show this. So you can do a bunch of stuff. Okay, for example, you can zoom in the data. Okay, if you see an outlier, okay, you can click and open the web page. In our case, each data is associated to a Catalina transient, and then we can go back, and we can choose to remove classes for the cylinders, or to remove cubes, cylinders, and things like that.
She was driving it in a solo mode, but this is written to be a shared visualization with multiple partners at different locations.
Yeah, actually I can give you the executable if you have a Mac or Windows, and you can connect to just through the IP address for now. You can connect, and I can run in broadcast mode, like here. And so whatever I do, you will see. And we can also chat. So I can remove my points, and you will. Now there is a limitation in this. That's the points are sent through internet.
And you
so
have access to it?
Huh?
And we can make changes, or not? Only you?
No, whoever is broadcasting. So I can release the button, you can press the button, and then you can send the broadcast.
For example, annotate, or for example.
Sorry?
I'm not allowed to make interactions.
Yeah, you are. I mean, if I'm broadcasting and you want to broadcast, you just tell me. I push again the button, so I release my broadcast, and you can press your button, and I'm going to see what you're doing on your.
So collaborators can agree who is going to be changing the data. It has to be done synchronously for all of them. And you can choose, however, to have your vantage point same as the person driving the visualization, or you can detach yourself and look from a different angle.
Yeah. And of course, there are small things like if you hover on a point, you can see some information here, and it can be whatever you have stored. For now, I'm just plotting the coordinates, but it could be ID, actual array and deck. Pretty much. So we can make also some cool stuff, like also making video games. You can shoot that supernova points.
Oh, come on.
You can chase and shoot them.
So
and
there is
this is done with the free version of the Unity platform.
So the idea is to have a web-based 3D data browser that you don't have to do anything for. It's to be just available to you. Then there'll be a little more sophisticated version later.
So is the color selection hardwired by the input data, or
no.
Can that be?
There is a standard format where which column will be represented how, as X, Y, Z, whatnot, and we can switch that internal to the graphics engine.
And the classes are encoded with colors. So you have the column that you call class. It has, I don't know, 1, 2, 3, and they are encoded with the shapes and colors.
For example, could you select a subset of these points and color them yellow?
You have to interact with the data file. There is no such option in the browser yet.
No.
Right.
Yeah, but that's possible.
So there's a fine line of how much you want data browser to do and become more clunky versus streamlined, and you just have a separate data prep program to learn, scale it however you wish. But the coordinates that are available to you are X, Y, Z, size, shape, color, which will be 1 or 2, brightness, transparency, and then beyond that, we're talking about the shapes of the points, I said, glyphs on the data points, or if they're not spherically symmetric, they can spin, or they can be oriented a different way. They can also pulsate at a different paces. Now, at that point, you have a raging headache. Right? So, yeah.
Maybe you just said this. How do you get the data in there? This is being set up by you, or this is something?
I know. I just loaded the data before. So
we now use plain ASCII or CSV files. We will have a VO table input as well.
The plan will be this cloud service, so you just point something on that web page at a local data file, and it will read it in. And then
yeah, you can read your own local data or data anywhere on the internet.
Do you have some kind of, will there be some kind of API where you can hook this up to other services and then generate data or pull data out of databases using some other cloud service? And
yes, well, give us some time, okay? This is not even alpha version yet.
Now, see, this is how we are loading now the data. Just copying and pasting the address here. And can be local file or HTTP.
But that's the ultimate one of the
goals, sure.
Right?
Yeah.
Other services.
Absolutely. Okay. So to conclude here, and then we can take some more questions. In addition to this, I mean, there is a whole number of technologies that are coming up, and 3D displays, of course, but there are haptic interfaces, and Kinect is the most prominent of them. I'm of the opinion that Kinect may be the single most important thing that Microsoft's ever done, because it's opening up a whole new paradigm of how to interact with cyberspace. Not just playing games, but interact with other people, interact with data, and so on. And there'll be a choice of whether people want to be represented as their own video version, 3D video version, or as avatars, or whatever. We are still learning how to use these technologies properly. But this is essentially science fiction coming to life, right? Seen in displays of data that are manipulated by hands. We can already start to do this with Kinect. In fact, we're working on Kinect thanks to input from Jonathan and others. And Jim also already pointed out this great little new piece of equipment called Oculus. And we have invested in that. We expect to get SDK for it in December. And so this will be a lightweight, easy way for complete 3D immersive sense of VR. Eventually, maybe we'll all have Google Glass or something equivalent that we can overlay augmentative or fully immersive VR on our vision. So that's where we're going. So the key points are here. I mean, visualization is probably the single most difficult problem we have now in massive data science, because you don't really understand things intuitively unless you can visualize them somehow. And we have problems not with just quantity, but complexity of the data, dimensionality, and so on. Another thing is, if there is one thing that I learned from playing with VR, is that we are totally meant to interact in 3D. We're optimized to interact in 3D. And so the whole two-dimensional display thing is obsolete artifact. And so this could conceivably lead to greater insights as we explore the data. Even so, I mean, there are still limitations to what brain can process. I said up to a dozen. That really is absolute maximum. Effectively, maybe 6, 7, or 8 dimensions are what you can comfortably deal with in display. So we now already have working tools that are free, available to anyone. You can do this on virtual world platforms. And we're developing this one that's web browser based, which I think will also be zero cost until we get into the goggles and stuff, in which case you have to pay money for those. But the goal is to be able to do fully immersive 3D visualization anywhere, on your laptop, desktop, at home, the airport, without any special equipment. Right. So that's it. Thank you.